Hello, you're welcome back. All right, so we are going to continue from where we stop. Okay, now previously we actually looked at separable ODE, how to evaluate separable ODE. Okay, ODE that the variables can be separated from each other, right? On which we actually give some examples. Okay, now a separable ODE is simply an ODE of the form. Okay, divide the x, all right, uh, equal to m being a function of x, m of x, then dot n of x. So if the function is of this nature, it can be separated. Okay, and of course, which we know that for us to separate the variable, please pardon me, n of x and n of y. All right, pardon this. Okay, the dependent and independent variable, so it can be separated. So I can do that by cross multiplying first. All right, if I cross multiply, I have m of x multiplied by n of y, then times the x. So I can now separate the variable, right? The function of y, okay, is separated, goes to the y, right? And of course the function of x goes to the x. So this is how we actually evaluated the ODE, okay, that can be separated, that the variables can be separated from each other. All right, but now we're going to be looking at some ODE, okay, that the variables cannot be separated. Okay, that simply means that the ODE has a function known as implicit function. Okay, now such ODE can be represented as dy dx, all right, equal to m x comma y, all right, then of course plus nx comma y. Okay, so this represents that this is an inseparable function of x and y, and of course it is also an inseparable function of x and y. So how do we solve an ODE that the variables cannot be separated? So we're going to look at different method and of course different ODE, okay, that we're going to solve, okay, using different method. And those ODE, their variables cannot be separated, right? Now we're going to look at the very first ODE. We're going to look at this, how to evaluate exact ODE. All right, so now exact ODE. The question is, when is an ODE said to be exact? Okay, now an ODE of the form ODE of the form, okay, m being a function of x and y, all right, multiply by d of x, then plus n, which is of course is also a function of x and y, all right, multiplied by dy, equal to 0. Now such ODE is said to be exact only if when I find the derivative of m with respect to dy, okay, m is a function that's attached to the x, and is a function that attached to the y. So if I should do the m with respect to the y, okay, and also do the n with respect to the x, okay, if they are equal, right, if the m all over the y and the n all over the x, if it's equal, then I can simply say that such this ODE is what? Exact ODE. And after testing, okay, the exactness of an ODE, we can solve it using a very simple formula. Okay, let's say the solution, let me call the solution u. So for me to solve an exact ODE, I use the simple formula. The integral value of m, right, with respect to x, then plus the constant of integration, and it happens that that constant is a function of y that I need to find. Okay, so by the time I integrate m, all right, of course m is a function that's attached to the x. Okay, then of course find this particular unknown function constant, which of course is a function of y, then that is my solution. Now for this to actually make sense, I'm going to bring in an example, right, so that you understand what I mean. Example. So the question is solve. Okay, so I have cos x plus y dx plus 3y square plus 2y, then plus cos x plus y, then multiply by the y. All right, so equal to 0. It's an equation, right? So now as you can see, this equation is of this form, all right, of the form. So what we need to test now is it an exact ODE, right? How do we test that? You know, from what we have here now, you should agree that m of course is the function that's attached to the x, which of course is cos x plus y. Then come out excuse me, n is a function that's attached to the y, which also is cos x plus y. And you know very well that if you find the derivative of m with respect to y, right, if I differentiate cos x plus y with respect to y, you know very well that I'll have minus sine x plus y. Okay, just in case the derivative, you're not conversant with derivative, I will advise you to go to the year 1 of this application and study calculus, right? Then you get to learn different differentiation technique. All right, so now let's do this. So this is going to be the n, okay, with respect to the x. If I do the n with respect to the x, I will have the same thing. That was going to be sine, okay, x plus y. All right, so now as you can see, this is equal to the m all over the y is equal to the n all over the s. So I can simply say that this integral, all right, is exact. This ODE, please pardon me, this ODE is exact. Okay, so having known that it's exact, it is easy now for me to solve it. So let the solution be u be equal to, okay, the formula is the integral value of m with respect to x, then plus a constant that I need to find. I will tell you how to get the constant, but first let's integrate. All right, so I'm going to integrate. Of course, you know my m here, m is cos x plus y with respect to the x, all right, plus k of y. All right, let's proceed. So my u is going to be equal to, let's integrate cos x plus y with respect to s. If I integrate cos x plus y, okay, definitely you know the integral value of cos is sine. That is going to give me sine x plus y. All right, then plus, if I integrate k with respect to y, okay, k is a function, I don't know what it is, so that will give me the k all over the y. Okay, please pardon me if I'm not integrating k. K is a constant, all right. I'm not integrating k. K is the constant of integration. Please pardon me. All right, so this is I'm gonna have this as my integral value of cos x plus y, then of course plus the k, right? Okay, so now with what I have there here, the question is how do I get this k, right? For me to be able to get the k, the unknown k, all right, I have to find the derivative of this expression, right, with respect to y. So I need to find the derivative du with respect to y, right? And of course, if I differentiate sine x plus y with respect to y, I will have cos x plus y. All right, and now this, if I differentiate k with respect to y, that will be what, the k all over the y. So remember, the whole idea is for me to find k. Now I'm gonna do comparison. Okay, I'm gonna compare what I have, this derivative of sine x plus y. Okay, this what I have here, which of course is cos x plus y plus the k all over the y, with what I was given in my original equation, right? You discover that my original equation has both cos x plus y, then plus another value attached to it, 3y squared plus 2y. Okay, so if I should compare, I can simply say that cos, okay, x plus y being a function, all right, has another function attached to it. Okay, that was 3y squared plus 2y. So if I should compare with this, it is also equivalent to, all right, it's also equivalent to having the same cos, all right, x plus y that I got when I differentiated this function, then plus another, okay, expression attached to it, which of course is derivative of k with respect to the y. So if I should compare variable, okay, I will say this is equivalent to this, right? Then the whole of this is equivalent to this. So I can now simply say that the k with respect to the y, okay, is equal to 3y squared then plus 2y. And you know exactly this, the whole idea of this is for me to actually get the value of k, right? And of course, looking at this now, this is actually an ODE. That for me to get k, I have to solve this ODE. Okay, the k all over the y is equal to 3y squared plus 2y, which I know that it can be separated. They say a separable ODE. So all I just need to do is just for me to cross multiply to separate the. So I can simply say that the k is gonna be equal to, all right, 3y squared, right, plus 2y, all multiplied by dy, right? So for me to find the k, I have to, all right, integrate both sides. You know how we do that, okay? With our separable ODE, you know how we have done that before, right? So of course, if I integrate the k is something as 1 the k with respect to, okay, 1 with respect to k, I will have k. Remember, if you integrate a constant, right, with respect to a particular variable, that will be that variable, right? Then of course, if I integrate 3y squared with respect to y, you know how we do that. That's gonna be 3y raised to power 2 power integration. In case you've forgotten this, go back to the tutorial of integration, right? This is the integral value of this, and of course, this is the integral value of this. Then divided by 1 plus 1, right? All right, so to get my k, now remember my k is only what is left for me, okay, before I could actually solve, okay, get the final answer of this ODE. Okay, so it's just I'm looking for this k, right? So now let's flow. As you can see here, the denominator has 2 plus 1, that's 3 divided by 3. Okay, so I'm left with y raised to power 2 plus 1, which is 3. Okay, so my k is y raised to power 3. Then of course here I have 2 plus 1 the denominator, then 2 cancels 2, then I'm left with y squared. Okay, so as you can see, this is now my k. So invariably now I can simply say that my final answer now, okay, of my solution is going to be equal to, of course, sine, all right, s plus y, remember, then plus the k that I'm looking for, that I just found, right? And that k is y cubed plus y squared. and that is it. All right, so I hope that is well understood. Don't worry. Okay, after the entire tutorial I'll still give more example, but this is how you solve. Once you see this kind of question, okay, this is how you solve it, by actually checking if it's exact. Okay, if it's an exact ODE, simply you apply this formula. All right, but question is, what if I have this a question that is of this form, but it is not eventually exact? If I test it, how do I solve it? All right, so now let's not actually proceed. Right, so let's look at a situation where you have non-exact ODE. Okay, non-exact ODE. What do you do in such a case? So anytime you're being given a non-exact ODE, all right, to solve it, simply convert it to exact. It is easy. Okay, you convert to what? Exact ODE. And how do you convert a non-exact ODE to exact ODE? You convert by multiplying a factor known as integrating factor. All right, now as usual, for me to illustrate this, for it to actually make sense, I'm gonna use an example. Okay, so example will make sense. All right, so now here we go. I'm gonna pick a question that will help us, okay, to understand this better. All right, so I have this question here. It goes like this. Okay, example, evaluate. So I have exponent of x plus y, right, plus y exponent y multiply by dx, then plus x exponent y, then minus 1 multiply by the y, of course, is equal to 0. All right, having seen this now, as you can see, this form of ODE, for me to solve it, I need to test, okay, the exactness of this ODE. Okay, and of course, you should agree with me that my m, right, is the function that's attached to the s, that's exponent x plus y, then plus y exponent y, and of course my n is the function that's attached to the y, which is x exponent y, then minus 1. All right, so how do we flow? We need to test exactness. Okay, test exactness of that ODE. And you know how we do that? By, okay, I'll do the m with respect to n. If I should find the derivative of please pardon me, I'll do the m with respect to y. Okay, I will differentiate m with respect to y, because y is the function attached to n, right? So if I should find the derivative of m with respect to y, I'll have, of course, if I the derivative of exponent, okay, of a function is still the exponent of that function, right? That's going to be exponent of x plus y, then plus, to find the derivative of y exponent y, remember there is a product function here, okay, that's y times exponent y. And of course, how to find the derivative of a product function is very simple. All right, you just keep one constant, okay, steady or constant, all right, one of the function, then you differentiate the other. So I'll keep y, then I differentiate exponent y. If I differentiate exponent y, I'll still have exponent y, okay, then plus, and now go the other way around. This time around, I'll keep exponent y, all right, constant, then I differentiate y, and of course if I differentiate y, I will have 1. So 1 times exponent y will still give me exponent y. So this is the derivative of the m all over the y, right? Okay, so now let's go to do the same for the n with respect to the x, right? Of course, if I'm integrating x exponent y with respect to x, the only thing that I'm going to integrate here is x, right? Because it's with respect to x. Okay, so this one exponent y, I'm not integrating with respect to y, so I'll just write it the way it is, right? So if I should differentiate x, okay, with respect to s, of course I'll have 1, okay, then 1 multiplied by exponent y, so I'm going to have exponent y, right? And of course if I should differentiate 1 with respect to x, if I differentiate the constant, it's always 0, okay? So this is my derivative. So you now discover that this is not equal to this. The m all over the y is not equal to the n all over the e. So I can simply say that this is not exact. So now, how do I now convert to exact? All right, so let's flow. For me to convert to exact, I must multiply everything in my original equation by a factor known as integrating factor, okay? I'll use I to represent it. And how do I get the integrating factor? Integrating factor is actually the exponent of the integral value of, okay, r dx, which mostly is a constant. R is a constant, okay? The exponent of r with respect to y, not x, okay? Please pardon me. Okay, so this is my integrating factor I. This is what if I should actually use this. Alright, if I should use whatever I have there to multiply the entire equation, then definitely it will convert it to exact. So the question is, how do I get this r, okay, of this function, of this expression, right? Now to get that r that I will need to integrate, right? The r is given by the formula the n all over the x, okay, which of course is the derivative of n all over the x, then minus the m all over the y, right? Then all divided by m. Already know we've gotten all those things, okay? We know our the m all over the y, and of course the n all over the s, okay? We know m. So let's flow with that. So that means my r now is gonna be the n all over the x. Of course, you know that's exponent y, right? That's exponent y. Then minus the m all over the y, which we did here, okay? Exponent x plus y exponent y plus exponent y, right? So exponent x plus y plus y exponent y, right? Plus exponent y. Close this bracket and of course close the outer bracket. Then all divided by m. And of course I will know our m, right? On exponent x plus y exponent y, right? Exponent x plus y plus y exponent y. Alright, so now let's run this. Let's do this. So at the numerator, you discover one thing, that minus will go into this bracket and convert everything to minus, okay? Everything inside this bracket will become minus. So I will still have minus exponent y here, okay? Collecting like times minus exponent y being outside the bracket, alright? Minus exponent y will give me 0. So I am only left with minus exponent x plus y, then minus into this, right? That's minus y exponent y. then divided by exponent x plus y, right? Then plus y exponent y. Let's flow. What I would do for me to be able to cancel this thing, okay, to divide this is, of course the numerator and denominator have the same thing, all right, but the only difference is that this plus here is not at as the numerator. So I will do something. I will factorize, all right. How do I factorize? I take the minus out, right? I factorize the minus out, then inside I will have exponent x plus y. Since minus is already outside, right? So in this minus here will be replaced to plus. Will replace by plus, right? So that will be plus y exponent y. Then divided by, right, exponent x plus y plus y exponent y. So as you can see now, they can actually cancel each other because they are the same to give me 1, right? So that my r now becomes minus 1, right? So now I can now get my integrating factor. Don't forget my integrating factor is what I need. Okay, the integrating factor is exponent, all right, minus the integral value of r, which of course is minus 1 with respect to the y. If I do this, this is going to be exponent. If I differentiate minus 1 with respect to y, all right, I will have minus y, all right? So please take note of that. All right, so this is my factor that I need to multiply to this original equation. So let me take that original equation so that I will do justice to that, all right? Okay, right. So I'll copy it. I bring it down here, and so you know what I'm going to do now? I'm applying exponent minus y to everything here, then it will be converted to exact integral. So I'm going to have exponent minus y, right? Then multiply by, let me use dot, exponent x plus y. Then plus, the same thing goes here, exponent minus y, then multiply by y exponent y. Then plus, the same thing happens here, exponent minus y, then multiply by x exponent y. Then the same thing, 1 multiplied by that will still give me exponent minus y multiplied by 1, which is still exponent minus y, okay? Don't forget our ds attached to it, okay? I'll just see myself, I just forgot that. Don't forget this dy attached to this equal to 0. So now let's evaluate this, right? Exponent minus y times exponent x plus y. Remember, this is indices, all right? Okay, with the same base, which is exponent, all right? So we write the exponent. Of course, you have to add, because it's multiplication, you have to add the powers. So adding the powers, minus y plus y will give me 0, okay? So I have exponent 0, which of course is 1. That will now be 1 times exponent x, right? Okay, so I have exponent 0 plus x, all right? 0 plus x is actually going to be exponent x, right? Then plus, this goes to the same process, okay? The base here is exponent here, I have exponent here, so I have exponent minus y plus y, which of course will give me exponent 0, right? And exponent 0 is 1, then 1 times y will give me y. So times the x, then plus, right? So in this case, exponent y, the same thing happens here. Exponent y times exponent y will give me exponent minus y plus y, right? Which is exponent 0. And exponent 0 is 1. 1 multiplied by x gives me x. Then of course, exponent x, okay? Then minus exponent minus y. dy, okay, dy equal to 0. All right, so what we have now, this we can now, after doing this now, we can now test whether this is exact now. All right, and so in this case, you know that m becomes exponent x, all right, plus y, and of course my n becomes x minus exponent minus y. All right, so let's test now the m with respect to the y. If I differentiate m with respect to y, you know what happens, okay? Okay, that simply means that I cannot, this function doesn't have y attached to it, all right? So I will ignore it. I'm only concentrating with this one that has y, all right? And that's if I differentiate y respect to differentiate y, right? I have 1, right? Then if I do the same here, the n differentiating n with respect to x. Of course, if I differentiate x, all right, I have 1, and I can't differentiate exponent because this is a function of y, all right? I can't differentiate it with respect to x. So that simply means that the m all over dy is equal to the n all over the s. So this is now exact. So since it says that now, it is easy for us to solve it, right? So for us to solve it, we apply our formula, okay, for the solution of exact integral, which of exact ODE, please pardon me, which of course is u is equal to m dx plus k. All right, so let's rule, which of course you know that my m, all right, okay, from my new equation is exponent s plus y. So that's gonna be exponent x then plus y, right? Remember, I'm differentiating with respect to x, then plus the constant I need to still find, right? All right, so I'm integrating, please pardon me, I'm integrating. So I'm integrating this with respect to the x. If I integrate exponent x with respect to the x, I will still have exponent x. All right, and if I should okay, am I making a mistake? I want to check if there's any mistake in my. All right, okay, I don't think I didn't see any mistake. So if I should integrate exponent x with respect to x, I will still have exponent x. And of course, if I should integrate y, all right, with respect to x, definitely this y here, okay, is something as 1y, all right? So I'm only interested in that constant coefficient 1, which I know that if you integrate a coefficient 1, all right, definitely you will have the variable, okay, that will give me xy. Now I was someone to ask, I'm not that someone question, the question I'm raising someone mind is, what happens when I actually integrated this, okay, with respect to y, then I had to ignore exponent x. Why don't I now? It's still the same thing. Exponent x something as 1 exponent x, okay? So the factor there, if I should integrate 1, which of course is the only factor that y can actually, if I should differentiate rather 1 exponent s, the one that's attached to the exponent, of course, when you differentiate a constant, all right, you know that you're going to have 0. So that's what made this to become 0. That's why I ignored it, all right, because exponent s is that's 1 exponent s, and when I differentiate 1, I have 0. But in terms of integration, okay, where you have y here is something as 1y, all right, and the integrating 1 is not gonna give me 0, it's gonna give me x, right? So that's why I'm having x then plus y, okay? So I hope that is well understood. Then plus my constant I need to find. All right, so this is actually my solution, but I need to get this constant. So how do I get this constant? I'll go back to my original equation to do compare and contracts. Okay. Okay, so I go back to my original equation. Then I'm going to do some comparison. Okay. All right, so now okay, I am not doing comparison now. Okay, the comparison is done after I must have differentiated. Okay, this is long, that is why sometimes you might end up missing some step. Okay, for me to get the care, I need to differentiate first. Okay, it's when I now differentiate this, what I have, right? Remember, what I have was as the integral of this exponent x plus s y, right? Then I still bring down my k. So I'm not comparing using u, I'm comparing, okay, with the derivative of u with respect to x. So please, all right, take note of that. So I have to find the derivative of u with respect to s. The derivative of exponent x, all right, with respect to y, please, rather, okay, derivative of u with respect to y, right? So if I should differentiate exponent x with respect to y, of course this is 1 exponent x, right, which will give me the derivative of 1 with respect to y, okay, is 0. So 0 multiplied by exponent x is 0. So this is gone, so I'm left with this. All right, now if I should find the derivative of y, okay, as you can see here, y with respect to y, all right, that is 1. Then 1 multiplied by x, that gives me x. All right, then of course plus, to find the derivative of this is decay respect to the y, right? The same step we actually took. So now with what we have now, remember I'm looking for k, it is now I can now do my comparison going to my original equation. All right, if I go to the original equation, okay, remember there's one part should have x, okay, because I have x plus a constant. Now if you look at it, is the end part. All right, the end part has x plus something attached to it. All right, so if I compare what I have, okay, at the end part, which of course the end, as you can see here, is x minus exponent s minus exponent minus y, is equivalent to what I did, what I have here as the derivative, okay, which still is x, okay, plus decay with respect to y. Right, okay, so let's flow. So comparing, I can simply say that x matches with x, okay, so k definitely will match with minus minus exponent minus y, right? So the k with respect to the y is equal to minus exponent of minus y. All right, of course, for me to get the k, now remember, all right, all I just need to do is to cross multiply and find the integral value of the right hand side, which of course is minus exponent minus y. And the integral value of minus exponent minus y with, okay, remember with respect to y, right, we still give me the same thing. All right, so I'm still gonna have minus exponent minus y. Okay, so have we got back here? So that makes my answer now u to be equal to exponent x plus xy, then plus by the k of y, all right, which I've actually evaluated, which of course gives me, so definitely this will be minus, okay, which gave me minus exponent minus y, right? So that is very simple, though the steps are long, okay? But if you do it, if you look at it over and over again, you get used to it. So please take note of that. All right, as we actually go. So now this method is how the method we employ, okay? Whenever we see an exact ODE or an ODE that can be converted to an exact form, all right? Okay, so please take note of that. Now we are still going to look at more general method of solving ODE of non-separable variable, all right? I'm going to bring up a particular an equation, all right? A general equation of ODE known as Bernoulli equation, right? Bernoulli equation. All right, so the general form of Bernoulli equation, okay, is actually an ODE of the form y prime, okay, plus. Now, before we even get to the general form, okay, Bernoulli equation, okay, can actually is used to represent it's an ODE equation, okay, which of course have different forms for both linear and non-linear, okay. So what I'm gonna look at, okay, is the Bernoulli form of linear ODE. Bernoulli form of linear ODE. So if it is linear ODE, all right, then Bernoulli equation goes this way: y prime, then plus p of x, of course function of x, okay, the same way we had m of x, function of x multiplied by y, then equal to q of x. So this is Bernoulli, okay, Bernoulli equation for linear ODE. So once you see this is the form. And of course, if we need to solve, okay, Bernoulli equation, all right, of linear ODE, it is just very easy, okay. We apply this general solution, which of course the general solution of this equation is given simply as, okay, the integral value of I, of course, of x, which of course that I of x is actually the integrating factor, which of course I'm going to show you how to I of x, okay, I'm going to show you how to find the I of x, then multiply by the q of x. The q of x is the function of x. Remember, that's a function of s at the right hand side, okay, then with respect to the x, then all divided by I, okay, the I of x, which of course is the integrating factor. Now let's look at a typical example so that it will make sense, right? Let's see example of how you are going, okay, example in which you are going to apply this equation, right? So example, let's look at this an equation where you are being asked to evaluate, all right, you are being asked to evaluate y prime plus x squared y equal to 2. Okay, so now the question now is, how does this relate to this? Okay, but first of all, you know very well that if I should actually compare this to my Bernoulli equation, right, which of course you know my Bernoulli equation is y prime plus p of x, right, multiplied by y, right, equal to q of x. So comparing this now, you now discover that p of x, all right, of course is a function that is attached to y, which of course is s squared. Then q of x is the function at the right hand side. Okay, so q of x here is equal to 2. All right, so at least I've gotten q of x in my formula, right? I've gotten the q of x in my formula. Now the question is, how do I get the I of x, the integrating factor? Simple. Okay, this time around the integrating factor still have the same, okay, formula. Remember, it's always the exponent of the integral value, but this time around it's gonna be the integral value of what? P of x. Since it's P of x, okay, then it's with respect to the x. All right, so now let's flow. So this is going to be the integral value of my P of x, of course, is s squared, right? Very good, with respect to the x. And of course, if I should integrate s squared, I have x raised to the power 3 divided by 3. Okay, so I'm going to have, so my integrating factor is what? S raised exponent x, right, raised to the power of 3. Okay, exponent x raised to the power of 3. Okay, I noticed something in this equation that was 3s squared. Okay, so please, the corrected form of this, that's 3s squared. Yeah, that's okay. So we simply mean that P of s is 3s squared, right? So 3s squared. All right, so I'm gonna have, of course, it's gonna be the same thing, right? 3x raised to the power of 3, right? All over 3, right? Then of course 3 cancels 3. So you now have that integrating factor is going to be equal to exponent x raised to the power of 3. Alright, so now we can now apply our formula. Don't forget our formula, okay? So having gotten that, now the solution to my equation now becomes, you know how it is, okay? The integral value of I of x, which of course is exponent s raised to the power 3, right? Then multiply by dot q of x. Q of x is 2 times 2 with respect to the x. Then, all right, okay, then divided by exponent, all right, the integrating factor, right, which of course is exponent s raised to the power 3. All right, so y now is going to be equal to, please, the same thing is applicable to, remember when we treated separable factor, I told you that if you are integrating the dependent variable, the not independent variable rather, okay, the s variable, remember you always have to introduce a constant. The same thing is applicable to this, right? So if you integrate this, of course, you know, if you actually integrate this is going to be 2, right? If I should integrate exponent, right, x raised to the power 3, the integral value of a function, right, still remains the integral value of that of the function. Okay, so I hope that is well understood. So I'm gonna have 2 exponent x raised to the power 3, all right, then of course plus a constant c, then divided by exponent x raised to the power 3. All right, so how do we evaluate this? So separating this fraction, okay, this is going to be 2 exponent x raised to the power 3 divided by exponent x raised to the power 3, then plus c divided by exponent x raised to the power 3. So this is going to be equal to exponent x raised to the power 3 cancel that. I have 2. Alright, then plus, then this exponent goes up, it becomes, that will be c exponent minus x raised to the power 3. Right, so this is my final answer to that particular question. Right, okay, I will still bring in more example. Let's look at another example. Okay, example. Okay, you have been asked to evaluate y prime, okay, plus y sine x equal to sine x. Alright, so comparing it to Bernoulli equation, you know that this is going to be y prime plus, alright, p of x, alright, multiplied by y equal to q of x. Okay, so this will make us believe that p of x, of course, is sine x, and of course q of x is still gonna be sine x. Alright, then with what we have now, don't forget that our formula, right, we need to get the integrating factor before we get our formula. So integrating factor I of s is going to be equal to exponent of, okay, integral value of sine x with respect to the x. Of course, the integral value of sine x, please take note of that, is always minus cos x. Alright, the integral value of sine x is always minus cos x. Alright, then bringing that now, getting our formula. So my solution now becomes the integral value, of course, you know, of I of s multiplied by q of x, right? I of s is exponent of minus cos x, right, multiplied by q of x. Q of x is my sine x. Remember, q of x, right? Well, q of x is sine x, right? So x, then all with respect to the x, of course, you know that already. Then divided by the integrating factor. Everything must be divided by the integrating factor, which of course is minus cos x. Okay, so if you look at this particular function here, the numerator, alright, when we treated integral value, okay, so that is called function of a differential function. How do I do that? Alright, how do I integrate this? If I should use u, okay, if I should say let u represent sine x, alright, if I go through, probably let me do that separately before I bring it up, okay, so that you can see. Okay, let's say I'm integrating exponent minus cos x, right, then sine x. You discover that the derivative of this function is actually gonna give me this function, right? Let's find out. If I say let u be equal to sine x, right, then definitely the u with respect to the x gives me cos x, right? Then if I should rearrange this equation, okay, to make the s the subject, right, if I should cross multiply to make the s the x, if I make the s the subject here, I cross multiply, alright, I will get to have the s be equal to du. Okay, please, let u, not use u is representing this, okay. Let u be equal to cos x, please pardon me, okay, not sin x. I'm going to use okay, remember sin x and cos x, okay, they are differential, okay, let's say opposite of each other, or counterpart of each other, okay. One yields the other, right? So I'm going to choose any one of them as my u so that it will cancel one. So if I should choose cos x, definitely after finding the derivative it will cancel sin x. So I will say let u, okay, be equal to cos x, right? Now if I do the u with respect to the x, all right, I'm gonna have minus sin x, all right. So now if I'm having the minus sin x, now that means my the x, if I make the x the subject formula, I'm gonna have, okay, du divided by minus sin x. So bringing it to this integral now, that's gonna be exponent of minus cos u, all right, it's gonna be minus, okay, remember cos x, minus cos s rather, okay, cos x has already been okay, represented by u, so that's gonna minus u, all right. Then of course sin x, then multiplied by the s, which of course is du, all over minus sin x, which you know that this cancels this, right? So you're left with, of course, minus will go at the back of integral. That's gonna be minus exponent of minus u with respect to u, right? Which of course, when you integrate minus u, you're still gonna have the function, okay? The integral value of minus u will still give me minus, will still give minus u, right? All right. Then of course plus c, so that's gonna be, and of course the u is cos x, right? So the final answer here, right, is gonna be minus exponent cos exponent minus cos x, okay. So this is just how you do that, okay. So you can do that in a rough, or possibly you can still, if you can combine it inside this solution, okay, solve it in the numerator, go through that process, okay, and you still at the end of the day your solution is not ambiguous, you can go ahead. But if not, you can just solve this, okay, the integral value of this in the rough, then bring it into the solution. So with what I have now know that, okay, the integral value of the whole of this is, okay, minus, right, that's minus exponent of minus cos x. Don't forget that I have to introduce c, all right, then all divided by exponent of minus cos x, right. So this is y is going to be equal to minus exponent, all right, of minus cos x divided by exponent of minus cos x, right. I'm separating the division, right. I'm separating division, then of course c divided by exponent of minus cos x. I just separated division because this is all divided by, so I separated this from this, okay. So at the end of the day, you know that this definitely will cancel this to give me minus 1, all right. So I'm having minus 1, and this will come up, right, to, I want to take this up, it's going to be c. So exponent of minus is a reciprocal, once it goes it becomes plus, right. That's going to be c exponent cos x, all right. So you can write it this way, you can write it this way, y is equal to c exponent cos x, then minus 1, and how you want to write it, okay. It still gives you the same answer, right. So I hope you are getting the technique, but if not, right, still go through the process again, you get used to it, okay. All right, so now this is how we apply what we've just applied. Now is, remember, Bernoulli equation, okay? And that was Bernoulli equation of ODE, all right, for linear ODE, right? But what if we have Bernoulli equation, okay, that we can use to represent nonlinear ODE? How do we solve for nonlinear? And how does it look like? Okay, a nonlinear ODE is of the form, okay, is the same, almost the same with the linear ODE, okay? Y prime plus P of X, okay, quite well, multiplied by Y, then equal to Q of X. Now the Q of X is not alone, right? It has the power of Y or a function of Y attached to it, okay? So, and of course that function of Y is like Y raised to power of, okay, a power. That's, I use N to represent it. So you know that this now is not the same with what I had before without Y raised power N attached to this, okay? So this, because of this Y raised power N attached to Q of X, this makes this equation now non-linear, right? So how do you evaluate such ODE? Because of course I can't apply this formula of Y equal to this divided by integrating factor. So for me to actually solve this, I need to linearize this, okay? How do I go through the process of linearizing this particular nonlinear ODE, right? I'm going to say introduce what is known as changing variable. What's changing variable? Okay, I will bring in u, let u, okay, represent a function that will end up removing this variable, right? So I'm gonna say a function y, which of course is y raised power 1, right? Then minus that particular power, right? Okay, so I will say the function that will remove this power, right? A function that will remove this power of this power, because I don't want y to have this power, all right, on it. So definitely I'm gonna do y raised power 1, okay, then minus n. I must introduce this particular function, all right? So if I do that, all right, if I say u equal to, let u be equal to y raised power 1 minus n, so what I need to do is first, okay, having changed this variable, I will differentiate u with respect to x, all right? If I should differentiate u, okay, with respect to x, remember the function here is a function of y. How can I differentiate a function of y, all right, with respect to x? That is where chain rule comes in, okay? Differentiating a function of y with respect to x is something as differentiating, all right, that function du, okay, differentiating this function with respect to y, then multiply it, all right, by differentiating y with respect to x. This is chain rule, all right? Chain rule. Why? Because if I should go through the process, y, the y cancel the y, I still have the u all over the x. So that's exactly what is going to happen here, okay? So this is the only way I can actually differentiate this with respect to x, all right? So now let's do that. So if I should do that, so that means simply du with respect to the x is going to be du with respect to the y, which of course we know, okay? You know how we do that? Power goes at the back of the function, which of course is 1 minus n, all right? Then multiply by y raised power 1 minus n, right? Then minus 1, all right? Okay, so if I should do this, of course you know that 1 minus 1, all right, will give me 0. So I am only left with 1 minus n, right, raised to the power of y minus y raised to the power minus n. So all I just need to do with what I have here, all right, I need to, okay, this is for, please pardon me, I didn't add the du dx. Okay, remember the u dx, the u dx is actually du dy, which I've done, all right, then multiplied by the word x. I didn't multiply this, okay, and of course I told that 1 minus 1 is 0, okay, so I'm having that du, right, with respect to the x is going to be equal to 1 minus n y raised to the power minus n, all right, then multiplied by the y dx, so that it will be easier for me to now find the y dx, all right, because I need to replace that in my original function. The y dx now becomes, okay, du dx, which of course, let me use u prime to represent it, du u prime, okay, divided by what I have there, that's 1 minus n, right, y raised to the power minus n. So all I just need to do is to represent this dy dx and of course y, all right, into the original, okay, equation. Once I do that, I will end up, okay, linearizing it. It will end up, it will be converted to a linear form. Now I don't want to, this is just an illustration. Let's actually get, okay, practical with an example. Okay, we'll get practical with an example. Let's look at, actually I want to get an example that will, okay, help us. Okay, so I have an example, right? Solve y prime equal to ay minus by square. Okay, so how does this work? Let's see how it works. Okay, how is this particular equation? First of all, right, if you look at this equation, you're gonna have, you notice that this is gonna be y prime. If I bring this to this other side of the equation, okay, ay, because I have minus ay, right, then of course equal to by square, as you can see, all right. So you can see now that this is of the form, okay, the form of non-linear, okay, equation of binomial, but because of the attachment of y raised to the power n to the function of q, and that's exactly what happened here, right? So the q function here is b, all right, this is q is the b, which of course is a constant. Then of course this is now y raised to the power 2 attached to it. Then this is actually, remember, this is p of x, right, which of course is a, have y attached to it, which is normal. Then so this is the nonlinear factor that makes that particular function to be nonlinear. All right, so remember what we do, change a variable for us to solve this. So we simply introduce u now will not be equal to y. You know how it is, y raised to the power 1, then minus that particular factor. If we should do this, okay, u is going to be equal to y raised to the power 1 minus 2 gives me minus 1, right? And you know the next thing we'll do is to do du. I would prefer du with respect to the x, right? So du with respect to the x, remember what it is, it's going to be du. I'll do du with respect to the y, which of course that's the function I see here, okay? Then I'm multiply by the y with respect to the x. Okay, so that's being said, I'm not gonna have u, all right, excuse me, so I'm not gonna have du with respect to the x, respect to x, okay, it's gonna be equal to, let's differentiate this. You know what we'll do now, that's gonna be minus 1 y raised power minus 1, that's minus 2, right? Then multiply by the y dx. So if that be the case now, remember, okay, the y dx now is going to be equal to, remember, the u ds, which of course I can, let me represent with u prime, right? All over minus 1, which of course is minus, right? Minus 1, that makes this fraction to be minus, right? Raised power, y raised power minus 2. Okay, so I know my dy dx. I also know my y. I will know my y from here, right? How do I get to know my y? I know my y from here, okay? How do I get to know my y? Remember, from what we have, u, okay, is equal to y minus 1. And of course, u is equal to y raised power minus 1, which is reciprocal. The same thing as saying 1 over y, right? So if I invert it, y will now be equal to 1 all over u. Okay, so I'm going to replace this, okay, the y dx and the y, okay. I'm going to substitute the two value, okay, into our main equation, into our ODE. All right, so let me bring that ODE again that we are solving, right? See the ODE, let me bring it. So I bring it here. All right, so let's go there. So this is gonna be y prime, which of course the y prime is the y ds, all right, is equal to, okay, I've not arranged this. I've not been arranged. Okay, let me arrange it. This was y prime, right? Then this goes over minus ay, right, equal to minus b y square. So substitute y prime, remember what it is, that's minus u prime, right, all over y raised power minus 2, which is something as y square. Okay, then minus ay, right, ay, all right, is equal to minus b y square. Now why do I keep it this way? Since I will definitely, for my derivative, okay, I don't always, my derivative shouldn't always have a function attached to the derivative, the dy ds. My please pardon me, my equation shouldn't have a function attached to the derivative, to the derivative, which of course is du with respect to the s. Okay, so I have to divide everything by y square so that I will eliminate y square all through. So I'm gonna have, okay, divide through, okay, by y square. So let's divide. If I divide this by y square cancel y square, I'll have, so I now have minus u prime, right? I believe that's what I had. I have, okay, minus u prime minus, all right, y square divided by y, all right, y square divided y, okay. I'm gonna have y, this y divided by y square, right? This can also have y in the denominator, that's y raised power minus 1, okay. So this is gonna give me a y raised power minus 1, okay. Then I'll equal to minus b square minus b multiplied by y square divided by y square cancel y square, I'm left with b. All right, now remember the whole idea of this. Okay, let's see, because one's supposed to have y attached to it, then the other. Okay, so let's see. So I'm going to I'm going to rearrange this equation, right? I'm definitely going to rearrange this equation so that it will be of this form, right? Minus u prime minus b comes over, becomes plus b, right? Then of course minus a y raised power minus 1, okay, goes over. All right, it becomes minus minus a, okay, why I'm introducing, please pardon me, I'm introducing u to this function. All right, so please pardon me at this point. Remember that 1 all over y is equal to u, right? That is what, so that's what I'm going to put here, okay, because everything will be in terms of u, right? So I'm going to have minus u prime minus a u, right, equal to minus b. Okay, so you know very well that everything here has minus. Okay, so if I use minus to multiply everything, multiply through, okay, I will have u prime plus u prime, then plus au, then plus b, right? So as you can see now, this now is linear. Okay, it is now linear. U being my derivative, right? A here being equivalent to p of x. Alright, my p of x is a, and of course my q of x becomes b. So my integrating factor, of course, you know what that's going to be, exponent of the integral value of a with respect to the x, okay, which if I do that, there's going to be exponent of the integral value of a with respect to the x. A is a constant, right? So that's going to be integral value of, that's going to be exponent ax. All right, so having gotten my integrating factor, now I can now solve the equation. So the equation now becomes y equal to, you know how we do that, okay, the integral value of the integrating factor, which of course is exponent ax multiplied by q of x, which of course is b, all with respect to the x, right? Then divided by my integrating factor exponent ax. All right, so you know, if this is a constant, right? If I should the constant still go at the back of an integral, right? Then if I should integrate exponent as is a function of a function, okay? And of course, anytime you are integrating a function of a function, what you will have, okay, is going to be exponent ax, all right, divided by the derivative of that linear function. Okay, so I will urge you to go and learn integration, of course, how to integrate function of a linear function. Okay, so that's gonna be exponent as divided by a. All right, then this is the integral value of this. Don't forget plus c, right? So all divided by my integrated factor, which is exponent ax. All right, so finally my equation now becomes, you know what is gonna be, okay, b all over a, right, exponent ax divided by exponent as I'm separating the division now, then plus c divided by exponent ax. C divided by exponent ax. So if I have this, you know what that's gonna be now? So this is gonna be, okay, please, this is u. Please pardon me, this is u, okay? This is u because I'm actually, the ODE is for u, right? The derivative of the ODE is for u. So let I bring the change of variable back, right? So it's for u. After I'm done evaluating that, then I'll bring the change of variable back, right? So exponent ax cos exponent ax, so I have b all over a, then plus c exponent minus ax. This is for you. Now don't forget that I was one I introduced u, okay? U originally is the reciprocal of y, right? So I can simply say that, okay, 1 all over y, which of course was u, is b all over a, then plus c exponent minus ax. All right, so of course if I should actually invert 1 all over y, I'll bring y up, then this will now be reciprocal of this. This is going to be 1 all over b all over a, okay, or better still, the reciprocal of the whole of this, yeah, 1 all over b all over a, right, then plus c exponent minus ax. So I hope that is well understood. Don't worry, we're going to look at more example, okay, after everything, but just go through the steps, understand the steps, and we'll look at more example, okay? So I'll give you the opportunity of going through this, then after you're done, then we'll look at more examples, okay? See you in the next video. Thank you.